toil and blood. Blackness was a virtue, the road was full of mud. I came in from the wilderness, creature void of form. And then she said, I'll give you shelter from the storm. And if I pass this way again, you can rest assured I will always do my best. For her I give my word. In a world of steel and death, and men fighting to be warm. And then she said, I'll give you shelter from the storm. And then she said, I'll give you shelter from the storm. Hey, what's up, you guys? Welcome to today's lesson for May 6th in general chemistry. So you can see we've got a lot of topics here to cover, and it's just kind of the nature of this last unit of Willamette Promise that's on solution set. It's got a lot of like different aspects of it. None of it's really hard, you guys, and the cool thing is that the test is open notes, right? So, we've got a lot of stuff to talk about here. All right, first thing is miscible versus immiscible. So miscible means this: when you have two liquids that can be dissolved into each other, especially in any proportion, they are called miscible. For example, carbonated water and orange juice. I can pour those together in any combination. 2 drops of orange juice, okay, a whole glass of carbonated water, 50-50, it doesn't matter. They're always mixable. That means they're miscible. All right, immiscible is the opposite, right? That means you cannot dissolve them together. So water and vegetable oil are immiscible. So the question is this: how do you know? Well, part of knowing that is understanding what a hydrogen bond is, an H bond, okay? So when hydrogen bonds with oxygen, fluorine, or nitrogen, you get what's called a polar bond or a polar molecule, right? So that means this, right? Since oxygen is a big hog, it will be negatively charged because it steals the electrons or doesn't share them as equally. And the hydrogen becomes positive charged, okay, because it's willing to give away those electrons to oxygen a little bit more. Okay, this causes a polar bond, like I said, positive and negative sides. And the positive and negative poles of different molecules attract to each other, right? Opposites attract. So what happens is the negative side of this water molecule is attracted to the positive of the other one, and we get what's called an H bond right here. Okay, if I can draw an arrow. All right, that would be an H bond. So an H bond, you guys, is an intermolecular bond. That means it happens between 2 separate molecules. Okay, it's not inside a molecule, it's between separate molecules. Now, H bonds kind of help us determine if things can be miscible or immiscible, right? If you can H bond with something else, you can mix. Let me show you what I mean here. So, like dissolves like is the thing we need to say. So that means polar molecules dissolve polar molecules. Okay, that means things that have H bonds. Okay, so water and methanol are miscible. So here's methanol right here, okay? And here's water. So we can see with methanol, we have an H bond right here where we have a positive hydrogen and a negative oxygen. So that means this negative pole on the water here is going to be attracted to this positive one on the hydrogen, the H bond on the methanol. Water and methanol are miscible because they can H bond. Nonpolar dissolve in nonpolar, okay? So remember, water is a polar molecule, okay? So is methanol. Well, here's hexane. Now, if you look at hexane, this is non-polar, right? So there's no hydrogen bonds on this guy because even though it has lots of hydrogens, none of them are attached to an oxygen, nitrogen, or fluorine. So that means there's no poles on this to be attracted to the poles, the opposite charges, on the water. So these would be immiscible with each other. All right, we're going to switch over to solubility of gases, you guys. Okay, gases can dissolve in liquids. We know that. We've got carbonated drinks. We've got oxygen and water. I mean, that's how this fish lives, is it absorbs oxygen that's dissolved in the water through its gills. There's 3 factors that affect the solubility of gases. They're all right here. So let's talk about them real quick. First is this, the size of the particle. Smaller particles are less soluble than larger particles. So oxygen is 8 times larger than a helium atom. Okay, that means oxygen is way more soluble in water than helium is. Okay, it's just kind of the way it is. If you want to know more about that, take AP Chem next year. Okay, cool. Just a little quick sell there. All right, the other thing is this: temperature. Higher temperature, the lower the solubility of gases, right? And this has everything to do with energy. The higher the temperature is, the more the particles in a substance are moving. So when you have gas particles with more energy, they're more likely to escape from the solution. Okay, just think of opening a warm versus a cold soda. Your warm soda is going to fizz a lot more than your cold soda. All right, this is the one we got to spend a little bit of time on, you guys. It's pressure. Specifically, we're going to talk about partial pressure. So partial pressure means this: it's the pressure of a particular gas in a mixture. Okay, that means this: every gas within a mixture has its own specific amount of pressure that it exerts. And the higher the partial pressure is, the greater the solubility. So check this out here. In this small little space of this carbonated drink, there's lots of carbon dioxide right now because we haven't opened the top, right? As soon as we open the top, that carbon dioxide is able to escape. And the amount of carbon dioxide in the air around us is a really small amount, less than 0.1%. So that means this: as soon as we take away all of that carbon dioxide partial pressure, bubbles appear and we get fizz, because the partial pressure of the carbon dioxide allows the bubble is less and it allows the bubbles to escape. This is like Red Rover, right? Right here, you've got a bunch of big, tough guys that you got to try and run through. It's not happening, right? Over here, we take away those big guys. All of a sudden, the person who's running, the gas in this case, is able to escape and get out. Pressure and solubility, you guys, are related to one another. Here's our equation right here. They are proportional, right? So here's our problem. Here's the molarity and the pressure, all right? What is the solubility at a pressure of 650 millimeters? Okay, if we reduce the pressure, we reduce the solubility, right? So here's our setup. The pressure on top here goes with the molarity, okay? And right down here, you guys, these two go together, all right? We do the math, and as predicted, when our pressure goes down, our solubility, our molarity goes down, right? Okay, if you're wondering what's the deal with pressure in millimeters, it's about millimeters mercury, you guys, and you can look that up online if you're super curious. I'm not going to take time here to explain it, though. All right, let's talk real quick here. Solubility of solids. Temperature does not always increase solubility, you guys. If you look at a lot of these lines, this is how many grams can dissolve in 100 milliliters or 100 grams of water. Most of the lines go up, right? But if you notice this one right here, okay, the cerium sulfate, it goes down. That has to do with energy and stuff like that. If you want to learn more about that, take AP Chem. Okay, but temperature does not always increase solubility with these solids. Now, what we can have here is we can have what's called a saturated solution. It's a solution that holds the max amount of solute. That means you can't dissolve any more in it, right? So what this does is it establishes equilibrium with the dissolved solid, and it dissolves what am I trying to say? Sorry. The amount that dissolves is equal to the amount of precipitate. So what happens is this, right? Once you get a saturated solution right here, say the solution is holding the maximum amount, right? Then you get anything that dissolves gets replaced by something that's in the solution, and we get what's called an equilibrium, or equal rates in each direction. Okay? Cool. One more thing on solubility of ionic solids. You can have what's called a supersaturated solution. So that means we've got a solution that's holding more than the normal amount. This makes it unstable. And the way you can kind of do this is this. Let's just take like this right here, the sodium nitrate, right, as an example. And at 20 degrees Celsius, right around here, we can hold about 87 grams per 100 milliliters, right? Okay, let's say I heat this up. I heat up the solution and I dissolve stuff in it. So let's say I heat it up to a temperature of like 70 degrees Celsius, right? Now I can dissolve like 134 grams in it. So I do that, and then I let the solution cool off back down to 20. It becomes what's called supersaturated. All right. when you have a supersaturated solution, it's unstable. Okay, so it's unstable, and at any moment, any little disturbance can cause it to boom, okay, start to form crystals. So for example, putting a stir rod in or putting a small crystal of something in can all of a sudden make that solidify and come out of solution, that supersaturated solution come out of solution quickly. Okay, cool. Now what I'm going to do is this, you guys, I'm going to make a second video that goes with this one. It's probably going to be a little bit shorter than this one, but it's going to explain a little bit more about some solutions, including parts per million and percent by weight volume.